Welcome, everybody, to webinar number 4. We certainly appreciate you joining us. Jeff, thank you for AGA for collaborating with this summer webinar series. I hope that everybody's enjoying it. I was part of webinar 1, where we talked about plate girders and W-shapes for simple span bridges. And during that one, I talked about some software that the Short Span Steel Bridge Alliance, or SSSBA, has developed to help owners and engineers quickly and very accurately come up with some designs for simple span steel bridges. So that's what I'm going to talk about, a few different products that the Alliance has. And then Eric joined me at the Purdue Road School a few months back, and we had a really great attendance and questions and discussion within that. And so Eric's going to talk on a contractor's perspective of building short span steel bridges. So today I'm going to talk a little bit about the Short Span Steel Bridge Alliance. Yes, we are a group of bridge and buried soil structure industry leaders who have joined together to provide educational information. Of course, that's today, right? On the design and construction of short span steel bridges. It involves all the stakeholders that are involved with short span steel bridges, whether it's, producers, manufacturers, prefabricated bridge people, universities, bridge owners, contractors, just everybody that's involved, including steel protection system folks. And this is what we deal with: buried bridges, rolled beam and plate girders, of course, the most common type of short span steel bridges. Press brake form tub girders, something that the Alliance was very involved with over the last 15 years. And then, of course, our members, our bridge manufacturers, develop very handsome and aesthetically pleasing truss bridges, whether they're for pedestrian bridges or vehicular bridges. And so what do we do? Well, we do a lot of education. This is part of that. We do workshops and webinars. There's a newsletter I'll show you right at the end. We have technical resources with standards, best practices. We're going to talk about the next one, simple design tools, E-span 140 and E-beam 140. And I'm even going to add another one there. And then we support anybody who has a need with the design or construction of short span steel bridges. And so when I go out and talk to people, whether it's county engineers or municipal or state or education at universities, I kind of bring it down to the 5 C's: cost, convenience, construction, county built, and carbon or sustainability. And I call that the 5 C's. Now, down there at the bottom, you see plus resiliency. And yes, I've done a lot of work on resiliency, but I can't figure out how to get the R to fit in with the 5 C's. But that circled one there under convenience, E-span 140, E-beam 140, and E-plate 140, that's what I'm talking about today. And we're going to start by just saying, hey, we know what our job is. We need to cross this creek in this picture with a simple span bridge. And we're going to say, because we've already done the hydraulic analysis and the flood analysis and things like that, we need an 80-foot long simple span bridge. And so what's decided by the owner or the owner's engineer is, yes, we need that 80-foot simple span composite steel bridge. We like 2 traffic lanes because it's kind of a rural bridge with a little bit high average daily traffic of 5,600 in one direction. But we like a 34-foot roadway width, and we like these Jersey barriers at 1 foot 3 inches, more or less wide. And so we see that bridge cross section that the user uses, or the serviceability part of this bridge, where we're going to have those traffic lanes, we're going to have the shoulders, and that's what our people drive across. And of course, what we need to do as the bridge engineer is we need to decide what goes under this service part of this bridge that meets all of the AASHTO requirements and expectations for durability and resiliency and design. And that's been an obstacle for steel bridges over the years. Not so much now, since the Short Span Steel Bridge Alliance and sometimes the National Steel Bridge Alliance has come in with some help on how to design that initial bridge. Because if we have to design that bridge, it's going to take some effort. And if it takes a design engineering firm to design that, starting with a blank piece of paper, then all of a sudden that's a real cost. Whereas some of the other materials, like a concrete bridge, we can look it up in a manual or a table or some procedure. And so the short span steel bridge lines developed what we call E-span 140, where we just designed, or we just came up and developed a bunch of standard designs from 20 foot to 140 foot for 4 different girder spacings. And it kind of designed the whole bridge, which means that in just a matter of a few moments, we could come up with a preliminary design for that 80-foot span bridge. We say preliminary because, of course, since these are standard designs, we had to be conservative on all aspects of that design. For instance, we had to assume the worst dead load cases and the worst overhang cases and the worst case for different loads and analysis to where it would cover everything. But this is a really good tool. It's been around for over a dozen years, and it's been used a lot to do preliminary design. And so, for instance, here's what it would do if we looked at an 80-foot span there with my red circle. It would give us a rolled beam solution. It would also give us a homogeneous plate girder, a 50 KSI plate girder solution. Now, it's also going to give us advice on press brake tub girders and buried bridges, but that's not what we're talking about today. We're talking about the rolled beam and the plate girder bridges here, and it would give us both of those. It's really easy to run. We on the left side here, we put in the span length. On the right side here, we put in the traffic lanes and the roadway width and the parapet width and the overhang width, and it's going to spit out a design for us that says this should meet even probably a little bit conservative, all the AASHTO requirements for a design for an 80-foot bridge. For instance, here we see the rolled beam. E-span right now is all composite design, but it would give us a composite rolled beam with 4 girders at 10-foot 6-inch spacing. And what it says is if you have a 20-foot diaphragm spacing, you're going to put in W36 by 2/10. Wow, we have an estimate for what that design would be in just a matter of a few moments. If we go to the plate girder, we can save weight, as we see here, because, of course, plate girders, we don't need to put the big top flange in there because that's near the neutral axis. We make the bottom flange a little bit bigger, and we can optimize the web a little bit better than those big, heavy W shapes. But it still says 4 girders at 10-foot 6, still 20-foot diaphragm spacing, and it gives us the top flange and the bottom flange to where in just a few moments, we can get, as shown here on the left side, for 4 girders spaced at 10-foot 6 with a 2-foot 6 overhang and those barriers, we get that plate girder design at the bottom left where we do transition the bottom flange to save some weight, and we have a constant top flange and we have a constant web, and that's a preliminary design for that plate girder. Now we can start pursuing that with additional studies or with a fabricator to see which is the better solution, either a W shape or a plate girder. And that was my talk a week ago, last Monday, was should we consider plate girders and W shapes for an 80-foot span? And I'm going to end with that today, but we're going to also talk about these methods to be able to come up with those designs. So that's this E-span 140. It's been around for a long time. It does need upgrading, and we're working on that with the SSSBA right now. That what's next is we are updating it to the AASHTO 10th edition. We're going to add non-composite bridges to that because a lot of our counties and maybe even some of our states still build non-composite steel girder bridges. And so they need a method to be able to estimate those quickly. And we're going to include additional solution options. For instance, what you saw was 4 girders at 10-foot 6. Well, we should also have, 5 girders at some spacing and 6 girders at some spacing, as counties like to do or states like to do. And this gets you into the ballpark. Like we say, it's preliminary. But we will release that soon. We just don't quite know when yet. We're working on it. But because of the success of eSpan 140, we developed eBeam 140, which is actually an Excel file design tool, which will optimize both non-composite and composite simple span rolled shape steel bridges. Now, this is the disclaimer that you'll see in the beginning, but this all is free and you can download it off our website, shortspansteelbridges.org. So what does it do? It does non-composite and composite design, and you can have all of these different yield stress steels in there. Now, the reason the 33 and the 36 are in there is because a lot of counties can get used beams from state projects, store them in their yard for a few years, and then use them for county bridges. And a lot of time those beams are 33 or 36 KSI. So that's in here. That'll meet the AASHTO requirements. And of course, then the more modern steels like the 50, the standard 50, and the coming 65 and 70s. But it is very flexible with bridge layout and diaphragm variable along the span. You can use any decking, non-composite wood, grid, corrugated metal deck, or non-composite concrete. Of course, composite concrete bridges can be used for vehicular loading. Of course, it does the AASHTO HL93. But one of the important things, it will also do a user-defined vehicle, like a logging truck or a state-specified vehicle. And then there's all sorts of user-defined characteristics. A huge strength of this eBeam 140 is that we can do a what-if analysis. We'll talk a little bit about that because it allows the user to investigate alternatives to where the starting design is. For instance, if we had a bridge where we had, like a 52-foot long bridge, we only had one diaphragm in the middle, and it gave us a specific design. What if we added a diaphragm? Would that reduce the steel enough to pay for and even save more money because we added that extra diaphragm? Or what if it called for a W36, a 36-inch beam, but a 27-inch beam had just a little bit more steel, but would really save us a lot of depth. And so what happens is during this design, we can see on the bottom left here, this is just an example design for that 52-foot long bridge, where it says a W36 by 135. Now on the bottom right, the program shows us from lightest to heaviest, all the W shapes that work. And yes, that W36 by 135 is on the top. But if we go a couple down, we see a W27 by 146. Okay, what is that? 11 pounds per foot more, but it saves 9 inches. And we know approach works expensive and abutment works expensive. And maybe saving 9 inches is going to way overcome the additional weight. And so the program allows us to play those games. And then, of course, it's going to give us a big summary page because eBeam 140 is not going to sign your documents. It's not a PE. Somebody's going to have to sign them. And so somebody's going to have to verify them. And so it gives us all the raw data and the developed design limit states, so the user can verify the design and sign it. Like on the far right there, it's got the service 2 limit state, and it's got the deflection and fatigue and strength 1 or 2, and then even the shear, and that's for the shear. And then kind of at the midpoint down, you have the strength design, strength 1 or strength 2, for the different, not necessarily unbraced lengths, but lengths of the beam. Here, there's those two 26-foot lengths. And it does the DC1 and DC2 and all that kind of stuff. And it calculates performance ratios for all those. It even does the construction load. We know construction is an important design limit state now for composite beams. And so we'll also do the construction limit state along with abutment reaction. So we can send that to the people that are going to be designing our abutment. Because we know because steel bridges are lighter than some other ones, we can save money on abutments. So here's what's happened with eBeam 140. It was released last September 2025. You can download it free. It is an optimized rolled shape design for composite and non-composite. It's been downloaded like 700 times. We're getting really good feedback on it from people that are using it. That says, hey, for instance, we had one person say, hey, I've got a bridge bundling project I want to bid, and I have 15 bridges on it. Well, in a matter of a morning, they were able to come up with very close to optimized designs for all of the simple span bridges in that bridge bundle, because all they had to do is put in the basic stuff and come up and use eBeam to come up with optimized designs. Okay, so that's been out there for not quite a year yet, and it's doing really well. And so the next step was, hey, well, almost all of you saw me talk or heard me talk about a week and a half ago about in the 60, 70, 80, 90-foot range, we should be considering both plate girders and W shapes for these simple span bridges. And so now we had, with eBeam 140, we had the W shape design taken care of. You can do it in a matter of minutes. How about the plate girders? And so my boss, Dan Snyder, the director of the Short Span Steel Bridge Alliance and vice president for construction for AASHTO, asked if we could develop one for plate girders. And I said, of course not. Plate girders have an infinite number of solutions. It's that, with W shapes, there's only so many W shapes, but with plate girders, we could have millions of different combinations. And I told him no, and he kept asking me. And finally, I decided, hey, let's try it. And we came up with it. It's pretty cool. We're real happy with it. It's not released publicly yet. It's going to be released here in 2026. But with plate girders, as this slide shows, is we can have an infinite number of solutions, more or less. And so we have to narrow that down. So on the top right in the green, we start with a target length over depth ratio. In some states and counties like to use 20, some others 25, some even go up to 30, but they can put that in there. And then the Excel program says, okay, I'm going to look at 5 different web depths, that target -2 all the way up to the target +6. And then it's got a whole file of flanges that meet all of the AASHTO and NSBA and collaboration document recommendations, like 12 inch by 3/4 inch minimum, and the tension flange has to be at least as big as the compression flange, and all those type of rules, to where for any one design, it's going to come up with 5,100 possible design combinations for the 5 different web depths. And that's the bottom right. You see that. It's going to list them from lightest to heaviest, where the top one there is a 13 by 3/4 top and a 38 by 1/2 inch web and 17 by 3/4 bottom. And then you have one right below it that's a little different, but still works, but is a little heavier. And we know plate girder design has a practical application to it. So the yellow on the left is where the engineer says, okay, yeah, I see all those solutions. Here's a practical one. And I just put in the top one there, 13 by 3/4 top flange, 38 by 1/2 inch bottom, web, and a 17 by 3/4 inch bottom flange. So that's a very typical composite plate girder bridge. And this is for an 80-foot span. And we see down below that yellow part where it talks about the strength and the service and the construction and the fatigue and the deflection design limit states and how it performs. And for the 4 different 20-foot sections in this bridge, it talks about how the strength and meets and the CB and all that kind of stuff. So that we can play that same what if game. What if we change the diaphragm spacing? What if we changed other than the lightest weight solution? What if we looked at readily available flanges and webs instead of what it selected as the lightest? And it's going to give us the same type of results that have to be verified by the engineer. But it gives us this in a matter of minutes. So like I said, it's not quite public yet. It's in the review stage. It is AASHTO 10th edition. It is composite and non-composite design, although I don't know of too many non-composite plate girder designs, but there is no reason that it could not be used. And so there is a user manuals developed right now. The examples are being developed. It's under industry review, and we're hoping to release it here in September 2026, just like we released E-beam 140 in September 2025. It is an optimized plate girder design. So last week, I talked about this study that in the mid-range, 60 foot to 100 foot, should we be considering both W shapes and plate girders? And back then I said I used E-beam for the W shapes and E-plate for the E-plate 140 for the plate girders. And then the fabricated cost came from DeLong's, one of our very efficient plate girder producing fabricators out of Jefferson City, Missouri. And in fact, Tanner from DeLong's gave the second part of that talk last week. And we looked at a 70-foot span, and we saw that for a W shape, it was a 36 by 160. And for a plate girder, we had a doubly symmetric, but flanges and webs. And that the plate girder was less tonnage, 12,000 pounds less. And of course, then we know plate girders have more fabrication processes than a W shape, but 12,000 pounds is a lot of steel saved. And we looked at an 80 foot and we came up with a W40 and a W36 because we know W40s have a premium price on them because there's only one producer that makes them. But we also saw that plate girder was 9,800 pounds less than the W40 and 10,800 less than the W36. But the reason I'm showing them here is these are done with E-beam and E-plate, and it took us like an hour to do all of these designs. Here's the 90 foot, again, a W40, W36. And again, now a singly symmetric plate girder comes in significantly less. And last week I showed that, yes, at least preliminarily for this initial study, we should be considering plate girders because the plate girders are less expensive than the W shapes, whether they're W36 or the 4044s, because it saves so much weight because we can optimize them. And when we get into those larger W shapes, their flanges are bigger and their webs are. And so we should be considering both. But that's not the reason I'm showing it today, other than to remind you of last week. The reason I'm showing it today was because we did these designs in a matter of an hour because of E-beam 140 and E-span 140. And of course, what we observed here was that the plate girder was less cost, and the premium on W40 makes it more expensive than the W36, even though it weighs less. But the big thing, the reason we're doing this study, as a reminder from last week, is that if we have a bridge out there and the W36 costs come in at 500,000 and concrete comes in at 450, because we are talking about steel bridges today, steel loses that bid and it's built out of concrete if all we do is consider W shapes. But if we also consider the plate girder that costs 22.7% less than those W shapes, all of a sudden steel wins with the plate girder. And we like that competition because that's going to make all bridge products better. And so this is what we're going to do with that study. But that's not the reason I showed it today. The reason I showed it today, because I showed this last week, the reason I showed it today was to show that we did those designs in a matter of just minutes with E-beam 140, which is optimized composite and non-composite rolled shape, and E-plate 140, which is optimized composite and non-composite plate girders. And these are free. E-plate 140 will come out a little later this year. We encourage you to use them on some of your past bridge projects or upcoming bridge projects to see if they can help you. And with that, I'm going to turn it over to Eric. But first, like last week, I encourage you to subscribe to the weekly newsletter. It comes out tomorrow or every Friday about 9:15 Eastern time. And of course, you can get the E-span and E-beam off here. You will be able to get the E-plate And we encourage you to visit the websites because we have so much information there. And with that, I'm going to turn it over to Eric Coburn, who is Vice President for Construction of Beatty Construction out of Indiana. And he's going to tell you how great it is to build steel bridges.
Yes, thank you, Dr. Barker.
You can go ahead and share.
Yep, bear with me. Okay, how are we looking here?
Don't see it yet.
It should be sharing. Is it sharing?
Okay, it looks like it's starting. There you
Okay.
go. We see it
Sorry about
perfect.
that, but we are rolling. So, thank you, Dr. Barker. As you mentioned, I'm Vice President for Beatty Construction out of Central Indiana. We are primarily a heavy highway contractor with our specialty on bridge work and deep foundations with elements such as earth retention, drilled shafts, auger cast piles, and the like. We primarily work on design bid build contracts, so keep that in mind as I present that someone has typically already used Dr. Barker software and determined that steel beams are the way to go. So we step in when we go to construct those. Here's a little map of where our typical work is. As I mentioned, we are primarily central Indiana with some work up north, south, east, and west, but this is where we do the majority of our projects. So I'm going to talk about a few case studies on some bridges that we have built and give some benefits that we have seen with steel beams. So the first one that I'll talk about is in Winchester, Indiana, State Road 32 in Randolph County. This is an NDOT, Indiana DOT project, and it involved the complete removal of an existing five-span flat slab bridge and constructing a new single-span bridge over the White River. It was a roughly $5 million project built in the first two quarters of 2024. So one of the main benefits that we saw here was this project was uh, in the middle of nowhere, if you will. And there were some challenges with some power poles and other elements with delivering long beams to the project. So this scenario, the beams were set to be spliced so we could deliver shorter beams to the job and then splice them on the project to create a single 133-foot long beam section. And then because of the lighter weight of these beams, we were able to handle all of these with a telehandler or an RT crane, which is equipment that we own and most contractors own. So it makes it a lot cheaper than having to rent heavy duty picking equipment. And then the next benefit that we saw was when it came time to set the beams. So with heavier beams, you would typically use two cranes to set. With this project, we used a single large crane, a 550-ton all-terrain crane, which having the single crane only moving one was significantly cheaper than the two cranes. And because of the single crane pick and the lighter weight, we were able to set behind the end bent instead of having to build a causeway into the river because of the savings of that installation, maintenance, and removing, plus the single crane, we estimated that that saved the project about $80,000. Next project we'll talk about is on the south side of Indianapolis. This is I-65 over Keystone Avenue, again, an Indiana DOT project. It was the replacement of a set of twin bridges done in phases. There were 9 steel beams per bridge at about 108-foot span. And this was a roughly $10 million project built in 2020. So a major component to this project being on an interstate was maintenance of traffic and how to construct the project. But due to the light weight of these steel beams, we only needed one medium-sized crane. That was a 250-ton all-terrain crane. And it sat down on Keystone Avenue with the beams staged beside it along Keystone Avenue. And because of this, we were able to do the work during the day, and we were able to do an entire bridge in a single day. Because that traffic control was minimal, we set up lane closures. We did very brief full stops when we actually set the beams and had minimal impact to the traveling public. We estimate about $20,000 in savings due to the limited maintenance of traffic. And a major component of that was, like I mentioned, that the beams were able to be set from Keystone. On a typical job like this, if you were using heavier beams, you would actually bring the beams in on the adjacent interstate with lane closures. So you're talking about major maintenance of traffic to set up lane closures on the interstate. Plus, you're only allowed to do that at night. And you'd have two cranes, one behind each end bent. So you start adding up all those issues along with the night work, and we estimate that steel beams on this project saved about $50,000 because of these aspects here, plus the 20 that I previously mentioned. So I've talked about a bridge over water and a bridge over road. So thought now we would talk about a bridge over a railroad. This project was in Wabash, Indiana. Again, Indiana DOT. This was a 130 foot. This was an at-road crossing, so this was a brand new bridge, 130 foot long over the railroad. About a $5 million project. We wrapped this up earlier this spring. So you've heard me say this before, but one of the major savings here was a single crane pick. So railroad policies require a 150% safety factor for lifts and do not allow for in-air handoffs between cranes. So that basically prevents you from using a lot of scenarios. So here we used a single crane pick, and we're able to sit back behind one end bent, and we estimate that that savings was about $80,000 on this project. Another component here is with being over a railroad, the clearance restrictions are very tight, and the shallower steel beams compared to some heavier beam alternatives allowed for the MSE wall to be built to the lowest elevation possible. So taller beams would have required more MSE wall, more fill, higher road elevation, which I did not get to estimate those impacts, but I think a lot of the designers would know that that was pretty significant savings there. Then another project we had, this is a much smaller job. This is a little county road project in Rush County, Indiana. It was the replacement of an existing box beam bridge with a 50-foot span steel beam bridge. It was a $1.5 million project completed in 2022. So one of the benefits here, one of the scenarios here was that it was a very narrow right of way and had very steep banks that you could not traverse equipment down to. So all the work had to be done back behind the end vents. So with these short span light steel beams, we were actually able to set them with an excavator instead of a crane. So major savings there with using our own equipment, not having to bring something in. So between not having to put in a causeway and maintain that, being behind the end bent and using an excavator, we estimate about $20,000 in savings on that project. So I know we're primarily here to talk about building new bridges, but I thought it would at least be worthwhile to mention a few benefits for rehabbing and replacing bridges when, our kids and our grandkids get to that point in these bridges' lifespans. So this is a project in Marion, Indiana. It involved the removal and replacement of the bridge deck on a 7-span bridge. It removed all end vents, all bearing assemblies via jack and support, and then the structural steel on the 2 outside spans. Those were um, about 44-foot long spans on those 2 exterior spans. So due to the lighter steel beams, we were able to use a pretty minor jack and support method here. I mean, you can see by the size of our supports that this is something that our employees could really just kind of manhandle into place as opposed to some of the much heavier jacking and supporting operations that we see. Again, similar story, small cranes behind the end vents. So we estimated about $20,000 in savings there. Now, one other kind of aspect here that was interesting is because we were matching to existing beams with the new beams, there were several instances where the existing bolt holes or notches, dimensions didn't perfectly line up with what was shown on the plans. So we had to do some welding, cutting, patching, heat straightening, which obviously would not have been able to be done with alternate types of beams. And then another project here on the demolition side. So this is on I-69 over 82nd Street on the northeast side of Indianapolis. It's the Clear Path project, one of the bigger projects that we've had in the metropolitan Indianapolis area. It involved the removal of 2 existing bridges and going back with 5 new bridges. This was about a $22 million job for just this bridge portion out of about a $500 million overall project. This is, fingers crossed, going to be wrapping up hopefully by the end of the month. So it's been a process, but we've learned a lot of good lessons on this one. So one interesting aspect with this on the steel beams over a pretty congested portion of road is that we were able to saw cut and slab the deck off with their very tight restrictions on what we could do with traffic underneath. So this method with the steel beams allowed us to do that much quicker and more efficiently than if if it had been on a concrete beam. You always worry when you're saw cutting on a concrete beam that you're going to get into the beam or you'll get into the hoops from the beam, and it's just not quite as safe. This is a pretty tried and true method, and it worked phenomenally well for us. Plus, you have a lot less cleanup of rubble and debris that falls down below, so it's safety for the traveling public, plus it's quicker construction. So with all of that, with the easier removal and picking up these light steel beams that we were able to pick with excavators instead of heavy cranes, we estimated that the demolition of these bridges was about $100,000 savings compared to what it could have been. So that is it from me, from the contractor's perspective of installing steel beams.